Yeah, so our next speaker is Matt Graham. Take it away when you're ready.
Yep. Hello, everyone. So this is going to be a little bit of shift in emphasis because I'm going to talk not about any novel methodology, but just purely about a software package. So I'm based at what's called the Advanced Research Computing Centre in University College London. And I'm going to talk to you about a package we've been working on for performing particle filtering in Julia and to distribute those computations on high performance computing systems. So this is all joint work. So it's been a collaboration between colleagues in UCL's Statistical Science Department, so Serge Golas and Alex Peskos, based there, and then also in ARC and Advanced Research Computing Centers, my colleagues Dan Giles, Mose Giordano, and Thomas Coscello have also worked on all of what I'm going to be talking about today. So just as a very high level motivation, so as all of you will be very familiar with, we're interested in being able to assimilate observational data in models of dynamical systems. And this obviously has very wide-ranging applications, so climate and numerical weather prediction. We're also interested in things like, and we're applying some of these methods to plasma physics within fusion energy modeling context. And we're interested specifically in particle filters, as they allow consistent inference in state space models when we have nonlinear dynamics and non-Gaussianity features. So our observation, and we'll be interested if people have got pushback against this, if they are aware of other packages which offer sort of robust implementations of particle filters that are able to be parallelized, is that although there are a few, there aren't that many that are kind of actively maintained, and in particular, there are not that many that are kind of easy to use for the end user. And so what I'm going to be talking about today is our attempt at starting to kind of develop a framework which we can build on. So all of this is with the proviso that, which many of you will be aware, that there are limits to particle filters and how they can be applied to sort of high-dimensional geophysical models. And what I'm going to be talking about is very much at the naive end of particle filtering methodology. In reality, to apply these at scale to the sort of models that we'd actually be interested in, we'll need to combine these sort of methods with things like spatial localization or tempering. But what we're interested in is building up the tools to allow us to get to that point. OK, so the package itself is written in a language called Julia, and I'll go into a bit more details about why we made that choice. One of the key things I'm going to emphasize is about the sort of development practices we're using. So the package is open source. Anyone can go and view the code up on GitHub. And importantly, it's well tested. So all of the different model and filter components have tests for correctness. And these are continuously run as we make changes to the code to ensure we're not breaking things. It's got automatically built documentation and benchmarking as well. We have tried to have a sort of well-defined, well-documented interface for people to integrate their own models. At the moment, as I said, we're at the very sort of early stages in terms of filtering and methods that we've actually got integrated. So we have the sort of naive bootstrap proposals and also locally optimal proposals for a more limited set of conditionally Gaussian state space models. The key thing that we've been trying to kind of integrate into the framework is the ability to work efficiently on high performance computing systems. And so we're supporting both distributed parallelism using the message passing interface MPI and shared memory parallelism using threads. So just to give you an idea of the sort of packages that I think are already out there, which do cover some of these similar sets of features. So there's the parallel data assimilation framework. So this was actually just recently released on GitHub. I think it had been previously, I think it wasn't closed source, but it didn't have it on a sort of standard source tracking system. This is a Fortran 90 code base. This is a nice package which has a much wider range of data assimilation methods than we currently have in ParticleDA. There is also this parallel particle filtering library, which has quite a lot of nice features and sort of clever use of parallel compute, and was originally written in Java. This package, as far as we could tell, is no longer actually developed. So it was There was a paper published associated with it in 2014. The code is still available, but there doesn't seem to be any kind of active maintenance or development of it. And this is the sort of thing that, like, this is a really nice package, but it hasn't sort of been maintained in use, and that leaves the code becoming difficult to use. And that's the sort of thing we want to avoid with ParticleDA. Okay, so I'm not going to go into any mathematical detail here. I'm sure many of you are already familiar with particle filters, but from the perspective of the software implementation, so we're throughout going to assume that the models of interest of working with are formulated state space models, so that we have a Markovian process driving the state dynamics, where the current state depends only on the state at the previous time step, and that our observations depend only on the state at the current time. The key thing embedded within these assumptions are that the model is fundamentally stochastic. And so when we're working with geophysical models that are deterministic, that involve solving some set of partial differential equations, say, these models will need to be augmented with stochastic updates to fit into this framework. And we'll look at, in a sort of climate and tsunami modeling context, 2 different ways we do this later on, hopefully. As a sort of illustration, just to put a little bit of a picture on that, what is a state space model? So this is the classic Lorentz chaotic attractor system. We have some state space, which we'll define in some vector space on the left here. Over time, I'll click on this, hopefully it'll work. We plot some trajectory through that, where our current state depends on in the previous state. And what we observe is possibly some partial observations of those state with noise. So what we get is effectively the data on the right. And what we're interested in when we're performing filtering is effectively inferring not only what the best fit trajectory is, but what this sort of distribution is on the underlying trajectory on the right. So particle filters are one particular approach for doing this. So they involve sequentially updating an ensemble of particles, whereby we alternate 2 steps. We propose new values for the particles from some proposal distribution. This is the main sort of algorithmic design choice within the algorithm. And then we resample the weighted particles to get a new uniformly weighted ensemble. So the key thing from an implementation perspective is that that first step can be trivially parallelized across each particle. And there's only a need for communication when we're doing that resampling step. So that's where often a lot of the effort will be driven to kind of getting efficient parallel implementations. Okay, so again, illustrating on that Lorentz example. So if we had some observational data, we would have some initial set of particle values that we sample from some distribution. We then iterate stepping forward in time and then resampling. So we see after we resample, we typically lose diversity in our ensemble, so it collapses down to a smaller number, but the weights represented by that histogram on the right become uniform. And here the orange is the underlying true trajectory that we originally generated the observations from. Red is the mean of the ensemble, and we see that we, with partial noisy observations here, we're able to recover the features of that trajectory. Okay. So why did we choose Julia to write this packaging? So this is a picture from a blog post by Matthias Cox, and it's, I think, a quite nice summary of this problem that sometimes gets called a two-language problem, but I think he actually terms it a two-culture problem. So there's a bit of disconnect between people who develop code mainly from the perspective of applying that code in some scientific problem or in some data analysis task. And typically, the sort of languages people will use here are things like MATLAB, Python, R, high level, often interpreted languages, where the code we can write is quite succinct, but there's often a performance loss there. And we contrast that with, say, software developers who are focused on performance aspects or adhering to best practices in terms of things like using design patterns. They will more often be using languages maybe like C++, Java, Rust. And often we have this issue that people will come up with some prototype in one of these high-level languages, but then they want to bring it to a sort of a more useful production scale. They'll need to start writing the performance critical parts of that implementation in some other language. So it's very common, for example, within Python to write performance critical parts in languages like C or Fortran. And that creates this disconnect when you're developing software. It makes it difficult for someone to have the expertise to kind of be able to develop the whole workflow. And Julia kind of posits itself as this kind of bridge between those two cultures. So it has a very high level syntax that looks a lot and shares a lot of features with things like Python and MATLAB. But it's a language which is very performant as well. And so you can write sort of low level code which is performant without needing to kind of call out to some other language. So yeah, to put a little bit more language on that. So it's a general purpose compiled programming language. It can be used interactively. So you can use it for an interpreter or a notebook interface. And in fact, this whole presentation is an example of what's called a Pluto notebook. You can also use it with the Jupyter notebook system that some of you may be familiar with if you use Python. So Julia is what's called just-in-time compiled. And so this is where a lot of that power comes from, the fact that we can write code which is specialized to particular types at the point that we need to actually run functions, but it also has things like automatic memory management as well, so we don't have to bother with kind of tracking and releasing memory resources. Sort of on the software development side, the key kind of programming paradigm within Julia is something that's called multiple dispatch. And this actually fits very nicely within this particular patch that we're developing. So it allows you to control the behavior of functions by the types of all of the arguments. And what this means is you can easily build up quite powerful behavior where you're composing different components together, but you get different behavior depending on how you're combining those components. So here we can imagine we have models of different types and filters of different types, and we want to be able to use those together in a way that we'll apply the appropriate filtering methodology with the models that we have. And multiple dispatch is quite a nice way of doing that. Okay, so a key thing that we've tried to emphasize is that we've went much more on having simple algorithms that are implemented well, rather than doing clever things where perhaps we're not able to test and to document as well. So we're trying to start from as simple as possible, and then once we're getting good performance and robustness there, to try and iterate from that. And so, yeah, as part of that, kind of getting back to what I said previously, so this is all open source, it's available on GitHub, provide a link at the end. We have a collaborative development model, so we're each reviewing each other's code, making sure that it adheres to good practice. There's automated testing of all of the code, documentation available for the application programming interface. And this last point, particularly keen to emphasize, so if anyone is interested in trying this out, we're very keen to get user feedback from anyone who's interested in using it. But also if anyone's interested in being involved in the development side, we're also very keen to get code contributions. So you can come in and speak to me afterwards if either of those appeal. Okay, it's going to spend a little bit of time just giving a high-level overview of how we've implemented the sort of parallel compute model within ParticleDA. So this is fundamentally going to be applied to parallelizing the computation of sampling from the proposal distributions and then computations of the particle weights. And the key thing to be able to get good performance on modern high-performance computing systems is to be flexible in how you deploy those computations to the hardware architectures. So typically, HPC systems now have complex hierarchies of processing elements, and the communication costs between elements at different levels of that hierarchy differ massively. And so we need to be able to control how different computations are associated with different processing elements, and so how those communication costs build. Just to kind of give a concrete example there, so Archer 2, which is the UK Tier 1 supercomputer system, it has a cluster of 5,000 compute nodes, each of which has a very complex hierarchy of processing elements. So we have 2 separate processors per node, which are individually connected with a fast interconnect, but then there's also fast interconnects going between the different nodes. Each processor then has separate what are called non-uniform memory access regions, where there's differing communication costs within pressing elements within these regions and across them. If we then break down further, we can keep iterating. We have what are called complex dies within those NUMA regions, and then core complexes within those complex dies. And we finally, if we iterate all the way down to the bottom, we get to the individual compute cores. And in total, that means that we have 128 cores for each node that we're working with. But there is this kind of complex hierarchy on top of that. That means that we can't just kind of treat this as one homogeneous mass. We need to be careful about how we split the communication across those cores. So what ParticleDA currently implements is a hybrid parallelism model where we both allow thread-based parallelism for use on shared memory architectures, where the communication is mediated by that shared memory, and distributed parallelism using what's called message passing interface, MPI, to allow, for example, communicating across separate nodes on a cluster or across different regions where there isn't shared memory on a particular node. Okay, so I'll skip over this. So to kind of get back to that high-level description of the algorithm where I was talking about earlier, if we have the particles each associated with, sorry, actually, maybe I should go back to this previous. So if we split the particles across here, ranks could be different processes on different nodes. And then within that, we will split the particles across different tasks, which we will schedule on different threads. And there is going to be one special rank, which does the overall coordination. And so in parallel, we can compute all of the proposals and compute the anomalized weights. And that's performed on both the coordinating rank 0, and all the other ranks. We then need to perform some communication to gather those weights to that central coordinating rank. So that happens as a communication step. We then do the resampling and then broadcasting of the resampled indices, which again involves communication. We do transfers of states between the different ranks. And then we do computations of statistics of the ensemble, which is done with an efficient reduction. So this is things like if we want to track, say, the mean or the variance or other statistics of our ensemble, that will involve some communication to do those summations effectively. Okay. I'm just going to give probably just this single example of applying this, and I'll wrap up. Okay, so this is a very simple model, which is kind of motivated by using in a tsunami tracking context. So here we have the idea of the linearized wave equation describing the surface height of water plus the underlying velocity field. And if we have some wave which is propagated from that bottom left corner, we'll see that it should move out. And what the idea is, we have a series of stations which allow us to noisily measure the surface height, but we have no direct information about the underlying velocity. And if I now look at doing filtering with this, so if we try this with, say, 100 particles, is this going to work? We see that if we effectively use a perfect sort of twinned model assumption, whereby we use the same model to generate the synthetic data as by which we use in the filtering case, we actually get quite good performance here, irrespective of the filter we use, and even with a relatively small number of particles. In fact, we can see that we're able to track this wave from a very sparse set of observations right across time. If we switch to a model mismatch setting where we don't assume that we know there's that initial wave being generated in this bottom corner, we'll see that actually we get much poorer performance, hopefully. Computer doesn't fall over. But we are still managing to do something we'll see with the locally optimal proposal. So we do still get the sort of coarse scale spatial features of that wavefront. But say using a bootstrap filter here, we're not able to do that. And that just comes down to the fact that the bootstrap is not able to exploit the observational information that we're getting here as well. And we get effectively weight degeneracy here in that the ensemble just loses any ability to capture the true distributions. Okay, so I'm, I think, pretty much at time. So I'm just going to, so this was just some plots to illustrate. This is applying it on tsunami model on R22, and we're able to get reasonable sort of parallel efficiency up to a certain number of ranks of independent processes. And you get differing performance depending on how you split that computation. So that was just to kind of illustrate that point, that it is important to be able to tie how you split the computation to the actual architecture you're running on. We also did apply this to a very simple weather model. We were able to successfully kind of integrate with that photon-nitride implementation of what's called a speedy model and get some reasonable results in assimilating here, example of assimilating surface pressure from a sparse observational network. And just showing here that if we look at comparisons of time averaged error in the ensemble with assimilation versus just running a naive simulation under the actual forward dynamics. So like cooler colors here represent lower errors. So this is just verifying that we are doing something useful. The simulation isn't just basically tracking because there's not enough uncertainty in the dynamics. Okay, so I'm going to wrap up. So I've talked about ParticleDA, which is a flexible package for performing particle filter-based data assimilation. The key thing that we think makes it attractive from a user perspective is that it has a very high-level interface. So it's simple to implement and integrate with your own models, but also to extend with further filter implementations. We have this relatively versatile two-level parallelism model, and we've been able to run this at scale on HPC systems, including R22. The sort of key next step is we're wanting to kind of move on to looking at implementing support for spatially localized filters, and we think this is going to be a really important aspect to get this to be able to work in practice on sort of more interesting scales of models where we've got dense observations, for example. Okay, so I think that's me. Thank you.
Thanks very much, Matt. We have time maybe for one quick question. Yeah, go ahead. So for online, is the resampling done for each node or across all nodes?
So at the moment, we just do it very naively. So we pull all of the unnormalized weights to that central coordinating rank. We then resample the particle indices on that rank, distribute the indices to the other ranks, and then we do point-to-point communication of the particles between the ranks that need to communicate the particles or replicate. And so there's nothing, as in, we know there's a lot of inefficiencies there, as we could be exploiting the known variation in communication costs to say solve some optimal transport problem, to just decrease the amount of communication we're doing there. But at the moment, as I said, we try to do a basics thing and get that working well before trying to do anything more clever. And actually, we found for now, with the sort of models that we're looking at, the copying of the states is not the major bottleneck. In fact, it's the load imbalance in previous steps, which is actually causing the main sort of decrease in parallel efficiency. So yeah, we hands up, we're not doing anything clever there. There are definitely better ways, and we're aware of. There's a lot of literature on improving efficiency of the resampling step in a parallel context. We're doing the sort of most naive thing possible, but actually we found at the moment it's not even then the bottleneck in the code.